Hello everyone. In today's lecture, we'll discuss about numerical differentiation. Differentiation is very important topic for engineers, and often engineers find differentiation very difficult as they need to remember many formula to do it. Okay, but when we use a numerical differentiation, the process of finding derivatives will become very simple. So in engineering, dy over dx is known as derivative, and in engineering mainly, whenever we write dy over dx, in the numerator the variable y is our dependent variable, whereas in denominator whatever variable we'll use, that will be our independent variable. It means if I write dy over dx in engineering, y is my dependent variable, x is my independent variable, and y depends on x. If I change x, the value of y will change. Okay, so let's see the simple definition. I don't go to the mathematical definition of limits using limits. Let's understand the derivative in a very simple manner. The simple definition of derivative dy over dx is nothing but change in y over change in x. Okay, both are with respect to each other. Like if I change the values of x, the respective change in y. Okay, so if for example if you take a dy over dx is equal to 5x plus 6, whenever you find dy over dx is equal to 5x plus 6, the meaning is very simple. When you change x from x1 to x2, okay, suppose there is a change in x from x1 to x2, then there will be a change in y from y1 to y2. Okay, and that change will be of the linear form, and that linear form represents your 5x plus 6. So in this fashion, this linear fashion, 5x plus 6, whenever you change y, whenever you change x, the change in y will be of this fashion, 5x plus 6. This is the simple definition of derivative. Okay, so applications of derivatives in engineering. Okay, to determine maximum and minimum values of particular functions. Many a times to find the maximum and minimum of a function, we need to find the derivatives, first derivative, and then we'll equate it to 0. Okay, like in the case of finding critical insulation, critical radius of insulation for cylinder, we find the derivative and we equate it to 0. We get, I remember, like critical radius of insulation of cylinder is k over h, where k is the thermal conductivity, h is the heat transfer coefficient. So whenever we want to find maximum and minimum of any function, we need to find the derivative. And the second application is when modeling the behavior of systems and processes. Means whenever we want to represent any system or process in mathematical form, okay, in mathematical form, we need to use the derivatives, because derivatives is nothing but represents the change of something with something. Okay, so whenever we want to write our mathematical models, this derivatives becomes a must. Okay, without derivatives we cannot easily represent any process or system in engineering. Okay, and you will see so many notations of derivatives. Whenever you take any textbook of engineering, you will find so many notations, different authors using different notations for derivatives. Let's see what are the different notations of derivatives. Okay, the first notation very we often use is dy over dx. Okay, and also del y over del x. We use dy over dx or del y over del x when change in x is very small. When change in x is very small, like 0.1 or 0.001 or 0.001, and change in x is very small, we use these two types of notations. Okay, remember, whenever we write dy over dx or del y over del x, only we will write when we use this notation when we want to say dx or change in x is very small. In thermodynamics, dy or dx is used to represent point functions like temperature, pressure, etc. Whereas del y over del x is used to represent path functions like work and energy transfer. Okay, so this is also the one type of difference. Okay, the main difference is we'll use these notations when x is where change in x is very small. Another notation we often use is delta y over delta x. Okay, this notation we will use when the change in whenever the change in x is significant. When the change in x is significant, we use delta y over delta x. Okay, so another notation of derivative is dou y over dou x. So whenever I write dou y over dou x, it means y partially depends on x. Okay, whereas when I write dy over dx, it means y completely depends on x. But whenever I write dou y over dou x, it means y partially depends on x. Okay, it means there is another parameter also on which y depends. That's why I'm using a partial notation dou y over dou x. Okay, and if we see the graphical uh, meaning, this is my x1 on x-axis. I took x1 and I took x2 very near to x1. Okay, so the difference in x2 minus x1 is very very small. Okay, and this is some arbitrary curve. Okay, some arbitrary curve I took, and I took x1 and x2 very near. So if I want to bring a relation between x1 and x2 and this y, I get a tangent to the curve. Okay, whenever dy over dx means a tangent to the curve. Okay, if I take x3 very far from x1, so that x3 minus x1, the difference in x3 minus x1 is significant, and if I want to bring a relation between this change in x and y, respective change in y, I will get a secant to the curve. Okay, so del y over delta x is my secant to the curve. Okay, so these are the graphical meaning. Dy over dx is tangent. Remember, x is delta x, change in x is very small. Delta y over delta x, the graphical meaning is secant to the curve, and delta x is significant.